Hi class. Alright, I have a question for you. Let's say you have a round bottom flask and you have a solution inside your round bottom flask and you have no idea what inside your flask. How would you figure out what is this solution inside your round bottom flask? To do that, to figure out what is inside your flask, you can use spectroscopy. The two spectroscopy techniques we're going to go over in the next few weeks is IR and NMR. Again, I want to talk about this for the next few weeks. What is IR, what is NMR? But right now, all I want you to know is that spectroscopy is going to help us figure out what we have in the flask. So aspirin, okay? What's the structure of aspirin? Aspirin is made from benzene ring and it has a carboxylic acid. How did we find out? How did we figure out the structure of aspirin? Spectroscopy. So what a spectroscopy does, it helps us know what is the exact chemical structure of different compounds, right? What is the exact structure of different compounds? For example, if you put aspirin in IR and NMR, it's going to tell you that it has a benzene ring, it has a carboxylic acid. Okay, so spectroscopy really matters in organic chemistry because it's going to help us figure out the exact structure of chemical compounds. So far, so good. All right. Like I said, we're going to go over IR and NMR later, but what I want to focus today, NMR, which we're going to go over the technique later, nuclear magnetic resonance. What NMR does, it gives you a peak for each unique set of protons. And this is all I'm going to go over today. Like I said before, I will go over what NMR is later exactly, but what I want to focus today, before we get into that, I want to go over the fact that NMR gives you a peak for each unique set of protons. And we're going to go over what this means. What does it mean that I'm going to get a peak for each unique set of protons? What does that mean? So far, so good? Okay. Now, let's go over what that means. Here is our first practice problem. And I'm going to show you that by doing a lot of practice problems. So this is propane, yeah? Now, here's what I want you to do. What I want you to do me a favor, actually draw the hydrogens out. I know you're all fancy and then you don't need to draw the hydrogens out, but let's go back to the basic. Draw out all the hydrogen for this propane. I'm going to do it, you do it too. Okay? Now what we're going to figure out? We're going to figure out how many unique set of protons does propane have. Basically, how many peaks am I going to see on an NMR for propane? Okay, you guys ready to do this? Now, these three hydrogens are attached to the same carbon. Do you agree? These three hydrogens are attached to the same carbon. And when you have a single bond has free rotation, right? It has a free rotation. So these three are equivalent to each other. They're attached to the same carbon, and when you have a single bond, there's free rotation. So all these three are equivalent to each other. So this is one set of unique protons. I want you to come over here. I have two hydrogens here that are attached to the same carbon, okay? That is another set of unique proton. And these two hydrogen attached to this carbon, and this carbon is attached to a CH3. So far, so good? Okay. Now, over here, I have three hydrogen. These are all attached to the same carbon, and so these are equivalent to each other. Okay. Now, is this a unique set of proton? This is actually not a unique set of proton because, pay attention to this. Over here, this CH3 was attached to a CH2. Over here, this CH3 is attached to a CH2. So this peak and these they have the same neighbor. So if these have exactly the same neighbor, what does that mean? These are equivalent to each other. Yeah? Okay. So again, let's go over this one more time. These peaks are equivalent to each other. They're attached to the same carbon, and when you have a single bond, there's free rotation. So these are equivalent to each other. This is one unique set of protons. Same here. I have another unique set of protons. 2 hydrogen attached to the same carbon, and then the neighboring is a CH3, CH3. Now these 3 hydrogen, equivalent to each other, attached to the same carbon. Now, they have exactly the same neighbor as these hydrogen. These hydrogen are attached to a CH2. These hydrogen also attached to a CH2. So these are equivalent to each other. So now, what does that mean? How many peaks are you going to see on an NMR spectrum for propane? You are going to see 2 peaks. You're going to see 1 peak for these ones, and you're going to see 1 peak for that. So we have 2 unique set of proton. You guys following so far? Okay. Now, one way to look for that, to make sure if these are equivalent or not, look for neighbors. Do they have the same neighbors? If you have the same neighbors, you're equivalent. Here, this is attached to a CH2, which is attached to a CH3. Here, this is the same thing. It's attached to a CH2, which is attached to a CH3. So they have the same neighbors. You have the same neighbor, you are equivalent to each other. Now, another way to know that is to look for symmetry. I'm not good with symmetry, but if you are good with symmetry, that's great. You should definitely also look at symmetry, because I have a symmetry right here, right? I have symmetry. If you can look for symmetry, you can see that these are equivalent to each other. There's a symmetry over here. These are exactly equivalent to each other. Almost like a mirror image. So far, so good? Okay, so we have 2 peaks for NMR for propane. Alright, yeah? On my race day, we're going to do a lot of practice problem to make sure that you're getting this down. So NMR is going to give you a peak for each unique set of protons. And we just did propane, and we decided that propane NMR is going to have 2 peaks for that. So when you're trying to figure out how many peaks you're going to have and how many unique set of protons you're going to have, here are a few things I want you to do. Draw the hydrogens out. I know you're all fancy now, you know organic chemistry, but draw the hydrogens out. Look for symmetry and look for neighbors. If they have the same neighbors, they're going to be the same. Alright, so here is our next one. This is one. Actually, I'm going to do a bunch of them. I'm going to put 2 of them out right now. This is another one. Okay, you ready? Let's do this. The same as before. I'm going to draw the hydrogens out. I know you guys are fancy and you don't need that, but I'm going, you know what I'm going to do actually? I'm going to draw it a little bit more to the middle of the board to make sure the lighting is okay. Yeah, to make sure you can see my lighting. Okay. Yeah, is that a little bit better? Maybe draw it again. There we go. Okay. Sorry, it's not easy to write on the board and trying to make it the camera at the same time. Alright, so what I'm going to do, I'm going to put the hydrogens out because that's going to help me out. Especially at the beginning. Okay, you ready to do this? Let's do this. These 3 hydrogen are equivalent to each other, right? I have a CH3, these 3 hydrogen are equivalent to each other. So far, so good. Okay, I'm going to name this A. Now, these hydrogens, this CH3 is attached to a CH2, attached to a CH2, attached to a CH3. So far, so good. Now, over here, these 2 hydrogen are attached to the same carbon. They're equivalent to each other. I'm going to name this one B. So far so good? Okay. Now, I have over here and I have over here. Hopefully right now, you are yelling at me that, whoa, look at that. There is symmetry going on here. Yeah? There is definitely a symmetry going on here. So, this peak is equivalent to this peak. And this peak over here is equivalent to this peak over here. Now again, keep in mind that you have a free rotation around the single bond. So you have the symmetry over here, and that means those two peaks are equivalent to the other two peaks. Okay? If you don't see the symmetry, you can also look at the neighbors, right? Look at the neighbors. Let's do this together. This peak, this unique set of protons, they're attached to a CH2, CH2, CH3. Attached to CH2, CH2, CH3. Now these peaks are exactly the same. They're attached to a CH2, CH2, CH3. So their neighbors are exactly the same, right? Their neighbors and neighbors of neighbors and neighbors of neighbors is exactly the same. So these are equivalent to each other. The same here. This one, the left neighbor is a CH3, the right neighbor is a CH2 as attached to a CH3. Now here, the right neighbor CH3, the left neighbor CH2 attached to a CH3. So they have the same neighbors. You have the same neighbors, you are going to be equivalent to each other. So how many peaks am I going to see on NMR for this? I'm going to see 2 peaks. I'm going to see 2 peaks on the NMR. Yeah? Okay. Good job. Hopefully you're getting the hang of this. Again, we just started this. We're going to do so many practice problems to make sure you get this done. Alright. This compound which has an aldehyde, I want to put the hydrogens down. How many unique sets of protons? Do me a favor. Pause me. I won't take it personal. Pause me. Do this. Unpause me. And then we're going to go over it together. This one for sure, right? I have a CH3 over there. Those are equivalent to each other. 1 unique set of protons. This one right here. Yeah, for sure. Now this one. Is this one the same as this? It is not, because they don't have the same neighbors, right? This one has a CH3 on one side and a CH2 on the other side. This one has a CH2 on one side and it has an aldehyde on the other side. So they have different neighbors. You have different neighbors, you are going to be different. Okay? Now, don't forget, this is another hydrogen, right? So we're looking for unique sets of hydrogen. This is a hydrogen for aldehyde. So how many unique peaks? We are going to get 4 peaks on the NMR. We're going to get 4 peaks on the NMR. So far so good? Okay, so you look for symmetry. There was no symmetry here. There was symmetry over there. Put the hydrogens down. Look for neighbors. They have the same neighbors. They're going to be equivalent. Ready for next one? All right. We're just going to keep doing this until you get the hang of this. So NMR is going to give you a peak for each set of unique protons. And now what we're doing today, we're going over to show you what I mean by unique sets of protons. Okay. This is one. And then this is another one. Alright, the first one. You guys ready? So what I'm going to do, if you're really good, if you're getting more comfortable, you don't have to put the hydrogen down. But if you want to, you can still put the hydrogen down. And I'm still going to put it out. But I'm sure you're going to get to the point that you're so good at this that you don't need the hydrogens. In the meantime, it's always good to put the hydrogens to make sure we don't lose any hydrogen. Alright, so what are you thinking? You're probably thinking that, okay, there's a unique set of protons right here, CH3, okay. Now, there is one hydrogen over here, that's unique, that's a CH, yeah, okay. We have a set over there, is this unique? Let's go over this. This CH3 is attached to a CH and then CH2 and CH3. This is exactly the same. This is attached to a CH, to a CH2, CH3. These two are attached to the same carbon. So these two are equivalent to each other. These two sets are equivalent to each other. They're not unique. Again, look for the neighbors. If they have the same neighbors, they are going to be equivalent. You guys are good so far? And again, keep in mind, there's also free rotation going on, right? Do you agree? There is a free rotation for single carbon-carbon single bond. So there's a free rotation going on. These are rotating all the time. These are definitely equivalent to each other. Okay? So I'm going to write this down. I want you to keep in mind that carbon-carbon single bond has a free rotation. They're rotating freely at room temperature, right? There's a free rotation going on. These are equivalent. They're the same. They're rotating at room temperature all the time, and they have the same neighbors. You guys are good so far? Okay. All right. Beautiful. So hopefully you agree that these are equivalent to each other, and then that one is another unique set. How about this one right here? Yeah. These CH2s for sure is a unique set because it's attached to a CH and CH3. Now how about this one? Is this a unique set? Yeah, this one is definitely a unique set. It's different than these two. These two are attached to a CH. This one is attached to a CH2. You have different neighbors. You are going to be a unique set. Alright, so how many peak? 1, 2, 3, and 4. I'm going to get 4 peaks on the NMR. I'm going to get 4 peaks on the NMR. Alright, ready for next one? Let's do it. Ooh, I give you a double bond. What does that mean? Put the hydrogens on. When you have a double bond, definitely put the hydrogens on. So I'm going to put the hydrogens on. Now here's what I need you to remember for double bond. Carbon-carbon single bond has free rotation around the carbon-carbon single bond at room temperature. Double bond, that's not the case. Carbon-carbon double bond, there is no free rotation. It's locked, right? There is no free rotation. It's locked. All right, so let's go over how many unique sets of proton do we have. One of them is definitely obvious, right? Over here. Everyone agrees that's a unique set of protons, right? Those 3 hydrogen are attached to this carbon, and then that carbon is attached to a double bond. So far, so good? Okay. Now, this one, is this unique? This is definitely unique, right? This and this are attached to the same carbon, but these are a CH3 attached to this. This is a CH attached to this double bond. Okay? Those are unique sets of proton. Now, let's come over here. Are these two equivalent to each other? What do you think? Are these two equivalent for each other? Do I put C or D? Or are they different? What do you think? So this one we know is unique. This one we know is unique. How about these two? They're attached to the same exact carbon. They both are 1 hydrogen. Are these two equivalent to each other? What do you think? Like a 50-50 chance. Okay. Before you answer me, I want you to think about this again. That carbon-carbon single bond has a free rotation. Carbon-carbon double bond, it does not. It's locked. Yeah? So because of that, when we have carbon-carbon double bond, because it's locked, the position is locked, and there's no free rotation, you have to care about what is cis and what is trans. So if cis and trans to each one is the same, then they're going to be the same. But if it's different, then there are going to be each set of unique protons. Now I want to tell you what I mean by that. You guys ready? Okay. Let's look at HC. CH3. Okay, let's look at HD. What is cis to HD? CH3. What is trans to HD? Trans over there, HB. So what they see when they look out the window are actually different. Their cis and trans is different. HC, the cis is a HB. For HD, the cis is a methyl. So are those unique or are they different? They are unique. They're not equivalent to each other because their cis and trans are different. And now why does that matter? If this was a single bond, that wouldn't matter because there's a free rotation, right? Sometimes you see this, sometimes you see this. Half the time you see that, half the time you see that. But when you have a double bond, you're locked. What you see for cis and what you see for trans doesn't change. It's exactly the same thing. So far so good, because there is no free rotation, nothing changing. So what is cis will always be the cis. There's no free rotation that they would switch places. So far so good? Okay. So the way I look at it, basically, when these two look out the window, they're going to see different things. So they're not going to be equivalent to each other. So how many peaks do we have? We're going to have 4 peaks. So double bond, you have to be very careful about because there is no free rotation. Ready for next 2? Yeah? All right. Very, very nice job so far. Beautiful job, actually. Okay. You ready to do more practice problem, yeah? Of course you are. Practice is good. Let's do 2 more. Let's do 2 more. And then these ones, I definitely want you to pause and do this on your own. And then we're going to go over them together. All right. The first one, if I look at the first one, I'm going to have, how many unique peaks do you think I'm going to get? So there's a CH3 over here. You know what? I'm going to follow my own advice and draw out all the hydrogens, okay? Yeah. I'm going to draw all the hydrogens. So I have 3 hydrogens here. I have 3 hydrogens here. Nothing there. Don't forget, carbon only has 4 bonds. I have a hydrogen here, and I have a hydrogen here. So far, so good? Okay. Beautiful. Let's see. How many unique sets of proton do we have? If you look at this, now before you do anything, I want you to look at this. And do you see any symmetry? You do, don't you? There is definitely a symmetry going on, right? Okay. So hopefully that's going to make it a little bit easier when you see the symmetry. But if you're not good at seeing the symmetry, let's go over each one anyway. So these 3 are attached to the same carbon. This is one unique set of proton. How about this one? Is this one unique or not unique? Well, let's see. What is cis to this? Hydrogen. What is trans to this? Hydrogen. What is cis to this one? Hydrogen. What is trans to this one? Hydrogen. Doesn't matter how you look at the window, in both cases you see hydrogen for cis and trans. So what does that mean? That means these 2 are equivalent to each other. Now, the other way to kind of look at it, there is a symmetry going on, right? There's a symmetry going on. These 2 are equivalent to each other. Now, let's go over here. Oh no, my red pen is... What do you think? Are these 2 equivalent to each other or not equivalent? The same thing. There was a symmetry over here, right? So they're equivalent. But let's go over based on the neighboring. If you can't see the symmetry, it might take a little time. HB. What is trans to HB? A methyl. What is cis to HB? A methyl. Let's look at the other HB. What is trans to it? Methyl. What is cis to it? Methyl. Doesn't matter how you look at it, doesn't matter which window you go to look at, you see the same thing. Your view from the window is the same thing. That's the way I look at it, right? So you have the same neighboring when you look at cis and trans. That means they're going to be equivalent to each other. So how many peaks on the NMR? You're going to have 2 peaks on the NMR. Okay, ready for last one? Last one is a good one, so definitely pause me and do this. I'm going to put the hydrogens out. Again, it really helps to put the hydrogens out. I have 2 hydrogens. Are they equivalent to each other or not equivalent? So what do you think? So here is a hydrogen over here, and I have a hydrogen over here. Okay? Let's look at the neighboring to see if they're equivalent or not. Let's look at this hydrogen. What is cis? Cl. What is trans? A hydrogen. What is cis? Cl. What is trans? Hydrogen. So when they look at the window, they see the same thing. Cis and trans are the same thing. So are they equivalent? Yes, they are equivalent. So I'm only going to see 1 peak. I'm only going to see 1 peak. Okay. This is just the start, okay? When we talked about the NMR, this is going to come back. I'm going to do more and more practice problem. But I needed you to notice before we get into the NMR and what NMR is and how to look at it. So NMR is going to give you a peak for each unique set of protons. Now, when you're deciding how many unique sets of protons you have, there are a few things I need you to do. Number 1, draw the hydrogens out. I know that's like basic, but that really helps. Draw the hydrogens out. Look for symmetry, right? Look for symmetry. And then look at the neighbors. If they have the same neighbors, then they are going to be equivalent to each other. And the last thing I need you to remember is that for carbon-carbon single bond, there's a free rotation. Carbon-carbon double bond is locked. There is no free rotation. So you really have to care about the cis and trans to see if they have the same neighbors, to see if they're equivalent. Yeah? Okay. All right. So we summarize that. Hopefully you guys are getting this down. All right. Nice job. But there's one more thing I want to talk about. And then I'll let you go. One more thing. And this is also going to help us to figure out the chemical structure. Remember, everything that we're doing is to figure out exact structure of chemical compounds, right? Exact structure of compound, we need to figure them out. So you probably had this in your classes before, the index of hydrogen deficiency. But I want to go over it because I want to make sure everyone is on the same page. So, number of hydrogen. How could you figure out how many hydrogen does an organic compound have? Here's the formula. Number of carbon times 2 plus 2, okay? Number of carbon times 2 plus 2 gives you the number of hydrogen. Then, what you are going to do, you're going to add 1 for every nitrogen that you have. You're going to subtract 1 for every halogen that you have, and you do nothing for oxygen. If you do that, then what you're going to get the number of hydrogen we have as long as we have nothing but single bonds. If it's saturated, that's what we get. So, let's go over this together. So to figure out how many hydrogen a compound is going to have is number of carbon times 2 plus 2. And then for every nitrogen, you're going to add 1. For every halogen, you're going to subtract 1 and do nothing for oxygen. What that gives you the total number of hydrogen that we have as long as we have single bonds. That gives you the total number of hydrogen that we have as long as we have only single bonds. So are you following me? Okay. Then, here is the deal. You subtract 2 hydrogen for each double bond, you subtract 2 hydrogen. You subtract 2 hydrogen for each ring. You subtract 4 hydrogen for each triple bond. TB for triple bond, okay? And lastly, you subtract 8 hydrogen for benzene ring. Let's go over together. So if I have just single bond, no double bond, no ring, is just single bond, is saturated, is number of carbon times 2 plus 2. If I happen to have a nitrogen, plus 1 for each nitrogen, minus 1 for each halogen, nothing for oxygen. That gives me the total number of hydrogen I have as long as I have a single bond. Now, when you have double bond, minus 2 hydrogen for each double bond. Triple bond, 4 hydrogen. Ring, minus 2 hydrogen. And the benzene ring, that's a lot of hydrogen you're going to lose. You're going to lose 8 hydrogen. We're good so far? Okay, beautiful. So, notice this is really going to help you out to figure out what a structure is, because the number of hydrogen is going to help us to figure out that do we have a single bond, do we have a double bond, do we have triple bonds in there, what do we have? Now let's do a practice problem with this. You ready for that? Okay, and this will be the last one, promise. So here is my structure. Here is my structure. We want to come up, without counting the hydrogen, how many hydrogen would this one have? You okay? Okay, let's do it. First, let's figure out how many carbons do we have, right? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So I have 9 carbons. I have 1 nitrogen. I have 1 oxygen. Now the question is, how many hydrogen am I going to have? I know you can just count. I know you can do that. But let's not count. Let's do based on the formula. You ready? So number of carbon is 9. Number of carbon times 2 plus 2. Do me a favor. I know you're good at math, but do not do math in your head during an exam. Because the simplest math during an exam, you can mess it up. 9 times 2 plus 2 is, oh boy, I wish I had a calculator right now. Is that 20? Yeah. That's 20 hydrogen, okay? Number of carbon times 2 plus 2. Now, for every nitrogen, I'm going to add 1. And I do nothing for oxygen. So 21 hydrogen is what I should have if it's saturated is just single bond. Okay? If there's nothing but single bond, I would have 21 hydrogen. Now, what I have a double bond over here. Do you agree? So I'm going to subtract 2 hydrogen. I have a benzene ring. I'm going to subtract 8 hydrogen. Okay? So how many hydrogen do I end up with? I'm going to end up with 11 hydrogen. I'm going to end up with 11 hydrogen. So far so good. I would have 21 if everything was single bond, right? But then I have a double bond, I have a benzene ring. I'm going to subtract those, so 11 hydrogen is what I'm looking for. Now, this is the part that kind of scares me a little bit. Let's put the hydrogens down and count the hydrogens. See if we get 11 hydrogen. You ready? Hopefully we get 11 hydrogen. Let's do it. 1, 2, 3, 4, 5. Nothing here. Carbon makes only 4 bonds. 6, 7, 8, 9, 10, and 11. Okay, the 11 hydrogen that we calculated, it matched up. So yeah, the 21 would be if there was no double bond, nothing at all. Everything is saturated. We only have single bond. And we subtract for a double bond, for a benzene ring. This is what we got. Sounds good? All right. beautiful job. Now what we're going to do in the next few lectures, we're going to go over iron NMR in detail, but I wanted you to have an idea of what do we mean by a unique set of proton when we talk about those. I will see you guys next time. Thanks for hanging in there with me.